Am I okay? Am I audible?
Yep.
Okay, great. So hello everyone. Today's speaker is Noah Holman, who's a PhD student at University of Freiburg and Berlin Institute of Health. He will be presenting CAAFE, which is a framework which uses LLMs for automated data science. This work will also be presented at NeurIPS this year. And so without further ado, I hand over to Noah.
Thank you. Yeah. So thanks a lot for coming today and for listening. If there's any question throughout the talk, I'm happy to be interrupted and just feel free to ask if something is unclear. So yeah, ever since I just talked about the generative AI hype really and large language models, ever since that got big last year, I was thinking there's so many applications of this to automated machine learning or automated data science. I was really excited about this, so I basically immediately started looking into how we can use this for tabular data learning, so to get better predictions on tables. I think some of the things that some of the challenges we had in doing that for feature engineering are applicable when you use LLMs for other use cases. So even if you're not thinking immediately about that, I think there are some interesting things that we found. So I'm just gonna start right into this. The title of our paper is large language models for automated data science, and kind of the question, I guess the first question is, what's the difference between automated data science and automated machine learning? I think this figure here is really useful from the State of Data Science from Anaconda, where they are visualizing how much time a data scientist is spending on all of these different tasks. I think this figure is being shared a lot. I hope it's actually accurate because I'm really surprised by this. But from what I hear, it's at least close to reality. We see that a lot of the time that data scientists spend is actually in data preparation, data cleaning, reporting, visualization, and the model building and model selection. These 9% blocks further down here aren't even taking up so much time. So if we think of automated data science, that's really taking up all of these steps in a data scientist pipeline. But automated machine learning is taking up a much smaller part of it, and I don't want to argue that automated machine learning isn't important. It's of course very important. I'm just saying that a lot of the time apparently that's being spent on tabular data prediction problems is actually in pre-processing and preparing that data. So I think that's kind of surprising. Why are we spending so much time why are we not working more on automated data science, which would entail all of these steps? And I think data pre-processing is also often part of the AutoML pipeline, but less so. So why aren't we working more on these other parts? And I think the reason for that would be that it's really hard, to automate feature engineering, pre-processing, data visualization, goal definition, insight generation, everything that goes around, because all of these steps, they actually depend on contextual and real-world information. So in order for a data set, answer the question, what's a really useful data visualization of the predictions of the importances in that data set, to create that plot, you need to know what the features mean. You need to know what goals of the user are and in which context the user is running the algorithm. And the same goes for feature engineering, which we tackled, where the goal is how can we transform and combine features in a meaningful way. Oftentimes, this question is much easier to answer when you know about the context of that data set. I think the reason why we it's really hard to automate that part is because we're lacking the contextual information and because the algorithms didn't really know about the real world, like all the small things that data scientists integrate in their work. And I think that with large language models, we do now have the tools to integrate much more of that knowledge into into our automated processes. So we see that actually, I would argue that LLMs, they have strength in this exploitation and data engineering part, everything that needs the domain knowledge, but in the last steps of the model building, algorithm selection, parameter tuning, I think maybe language models will be helpful there as well, but I think we have good tools to answer these questions, and maybe their classical methods and classical AutoML is actually really strong. Give me a second. Model building part. But I think it's more impactful. It's very impactful and strong, and I think it can profit a lot from the combination of LLMs and classical algorithms. Those can interact really well, and that was the idea behind CAAFE. So I'm going to show a quick demonstration of what the final result is. So here we see we have a data set with a CAAFE classifier, and we have a dataset description, which is here the dataset description variable. We're putting that into our CAAFE classifier. We're specifying the target column. We're enabling CAAFE, and then we have a dataset, which is a pandas data frame that has the feature names and everything specified. So we're inserting that, and the dataset description is that it's actually about predicting who will survive in a spaceship crash. So this is a dataset from Kaggle. We're giving this entire information to CAAFE, and then CAAFE starts generating additional features by combining and like applying functions to the original dataset. So for example, here we have a feature on the deck, and that feature splits the cabin string, which is some more complex format, into different parts, and it is recognized that the first letter of that string is about the cabin. I think that was written in the description above, and it can extract that information. In the next step, it does the same on the passenger ID, and it generates more and more features that are based on the textual description and also on what the dataset looks like. And what's also happening here is that CAAFE measures the performance before adding that feature and after adding that feature. And it checks if adding this feature actually leads to an improvement in ROC AUC or whichever metric you define. So here's this idea that we have to combine these classical algorithms with the large language model. The large language model is basically generating these hypotheses, being creative and generating code, but oftentimes that code is actually wrong or useless. And in that case, we have the classical algorithm, which checks through cross-validation if that feature generation makes sense or if it doesn't. So after a few generations, we measure the final performance, and we get like the aggregated code, which only contains all the features that were kept for that data set. So here's also, again, this kind of interface where the CAAFE classifier, which receives the column names, and that kind of enhances the base classifier. So let me zoom back or go back a step and like go a bit deeper into the question, why does feature engineering actually help? I think it's not entirely clear. why combining the features that are there already makes sense. The intuition behind that is that you generate a mapping to a new space, and in that new space, the problem is much easier solved. And in this example here, we have a data set that is completely without context. The green dot is what we're trying to predict, and the blue dots are labeled as true, the red dots are labeled as false. So from this, it's really hard to know if the green dot is true or false. If you were a prediction algorithm yourself, like I think it would be hard to make a prediction on that. But if you're now given the context of that data set, it becomes clear how you can create a new feature that makes the problem much simpler to solve. So now if you know those are actually days, and you know some of them are weekdays, some are weekends, and the question is, when is the person working or not? It's quite easy to classify this green dot given the context. So in CAAFE, as we just saw in this video, the user specifies the problem context and the dataset, so there's the dataset description and the feature names. And then the LLM generates code for this feature generation. The interpreter executes that code and transforms the dataset. Then we have this base classifier model, which performs cross-validation and checks if the engineering on the dataset actually helped or not. If it helped, the code is kept, and we are doing the cycle again on the transformed dataset, and doing this as many rounds as we like, or there's actually statistical tests or ideas that we can apply on how many rounds we should do that. So going a bit more into detail for this, just have to move the camera view. For this dataset, it's a tic-tac-toe dataset. We have a dataset description. And from this dataset description and the dataset, we're actually generating a really long prompt on information about the dataset, nonce in there, what some of the samples look like, data types, and the names of the features. And then we are describing how the feature generation algorithm would look like, and in which format we want the code to be returned. And here, I think what's a bit interesting is that we're asking the algorithm not only to return us code that does feature engineering, but we're also asking it to provide a name and a description of why this generated feature would be useful, and also print some of the input samples that would go into the feature engineering step. So in that way, the user afterwards has an explanation for why a feature was generated, and can actually control the algorithm, understand it, and also give hints on how to improve it. But it's also this idea that stepwise decoding of LLMs helps, that it's kind of a chain of thought decoding mechanism, where when the algorithm is asked to first give explanations on why something works, then it's going to give better results if it can access that information afterwards. So we're first asking it to provide information about the usefulness, and then generate the actual code for that. So after this first step, generating the first feature, we're getting this response from the algorithm. It has generated a column called number of X wins, number of ways X can win the board. It has given us a small string on why this would be useful, and it has provided us with examples of data that would go into that function. And we see it's actually a really long string that combines a lot of fields in our data set. And in this case, this was a really, really useful feature. It's kind of cherry-picked, to be honest. We see that after adding that feature, the dataset is already almost perfectly solved. And what happens then is that algorithm, the large language model, gets back this information on how much this feature helped, if it was used to transform the data. And depending on that, it will then in the next step generate new features and go in the cycle. So the LLM actually also gets that feedback for the next step of feature generation. And I think what was kind of interesting in working on this was finding a way in which we can benchmark this. So the problem is that the LLMs that are available, they are even often closed LLMs like GPT-4, which we used in our research. And even if they are not closed, it's really hard to find out what data was exactly used to train them. So if we look at data sets that are really popular in the research community, like balanced scale, like all these standard data sets that are usually evaluated, we can assume that those were actually a part of the training of the LLM. If we do a quick check, it's not like the LLM remembers those data sets, but we can see that it has heard of them and has probably also seen other people working on that data set and working to transform that data set. So it's hard to have an unbiased evaluation of these algorithms. What we did was we said, well, those data sets, they aren't perfect. Probably the algorithm has seen them in some way before, but we want that statistical power. We want additional data sets that we can run evaluation on. So we are keeping them as a separate evaluation set. And then we also added some data sets from Kaggle that are behind a wall of having to accept a license, having and those were also only released after the official end of the training data of GPT-4. So we tried to build this twofold safety mechanism that it wasn't actually used in GPT-4, but even then we can't be entirely sure about that. And I think that's definitely a problem when we are making research with these algorithms, finding sets that are unbiased that we can do our evaluation on. So when we try this, and we take the descriptions from OpenML for a lot of these data sets and feed them in there, and then for these Kaggle data sets, we take the Kaggle description. We see that running it with GPT 3.5, it helps for some of the data sets, but it's much worse than actually running it with GPT-4, which generates much better features than the original, or like without feature generation, we're getting much better results. And that is especially true for some of the data sets. So I think there's some really strong ones in here, like the tic-tac-toe data set. We see we get a huge improvement here in ROC AUC. And so we see also that this really depends very much on the data set as well, how much it's going to help to do that feature generation. If we look at basically taking different base algorithms and combining them with CAAFE, we see that for all the base algorithms, so if we take logistic regression as like our final classifier, random forest, AutoScaler, AutoGluon, tabular, we see that for all of them, GPT-4 with CAAFE is really outperforming here. But we also, and I think that's really interesting, we also see that other feature generation algorithms, these baselines here, they don't really help a lot for the automated machine learning algorithms. And so those are AutoScaler, AutoGluon, and tabular. And that's probably because these algorithms, they already do some kind of feature engineering, and they are already optimized to handle non-engineered data. So here it doesn't help so much to apply feature engineering. but it's a bit different for CAAFE, because CAAFE adds the semantic information to the algorithm, and that's not something that automated machine learning frameworks do at the moment by themselves. So we can actually see that with CAAFE, we are also having large improvements for automated machine learning methods. If we look a bit more into the feature extension strategies that CAAFE employs, we can kind of understand a bit better what it actually does. So we see that CAAFE can combine features in a meaningful way. So here we have a feature, fever and rhinorrhea, which checks if the temperature is higher than 38 degrees Celsius, and there's rhinorrhea. So this is kind of a meaningful combination according to the algorithm. That would be one of the most common symptoms of respiratory infections. So it kind of convinces you also that this is a useful combination of features. There can be this binning where the LLM bins different data points in different classes. So we see there's maybe the age of 18 is probably a meaningful age, or 21 in other places where you are kind of making this transition from a child or a teen to an adult. And that is the real-world information that only LLMs can integrate into an algorithm. And oftentimes it's actually a meaningful contextual information for the downstream algorithm. We can have these string transformations, which we have seen before. Also, CAAFE does sometimes drop features. So when these features were already used as part of other features in the feature engineering, we can drop them afterwards because they are maybe redundant. And we also see that CAAFE can recover from errors. So what happens when the code fails, we're just sending that signal back to the LLM, and then in the next generation, maybe it corrects that error. And we saw that actually in our datasets that the errors always get corrected. So maybe it missed that there can be nans, so missing values in the dataset, and then it gets the error that there was a float, and it will fix that error by filling nans. So I think it's also important to talk about the ethical and safety considerations of LLM work, but also our applications of that LLM work, like CAAFE is an application of LLMs. I think the automated code generation and the execution of that code is something that we have to be a bit cautious of. There is now so many works out there that are just doing this, like AutoGPT and also OpenAI's code interpreter. But we wanted to take a really safe approach to this automated code execution. So what we're doing is we added a list of operations that are permitted to execute, and every operation that's not part of this list of operations we don't allow. So this white list of operation only includes operations in pandas and NumPy that aren't accessing your disk. So it's just means, aggregations, and those kind of things, but it couldn't start running a shell script on your system or anything that accesses your disk. I mean, like, I think a whitelist is one of the safest way to do things, but even there, I'm saying it couldn't, but I don't know what actually could happen. I think even there's some leftover risk with executing code from an LLM. Also, we have this model interpretability issue. Machine learning algorithms are already hard to interpret, why they give some predictions and not another. But now we are putting this additional layer of the LLM on top of the predictions. And I think that can make it even harder to interpret. At the same time, the LLM is giving you these explanations for why features are generated. So that can add some interpretability at least. And sometimes the kind of generating more features and disentangling the feature space can help us to easier understand what's going on. Kind of going in the direction of this interpretability issues, also the replication of biases. When we apply a machine learning algorithm to data, like some tabular data set making predictions on it, we have, I would argue, two sources of bias. We have the algorithm that we apply, and we also have the data that is applied on. So if a data set contains biases that some group in the population is getting less access to a credit, for example, that could be replicated by that algorithm as well. But now we are putting a third level of bias on top of the algorithm, because the LLM also was trained on biased text data. So maybe, and we have an example here, it adds new biases. So I think this is a kind of really stupid example. You wouldn't want to do a task like that, but we just did it to show how biases can arise. So here the idea is asking the data, asking CAAFE to classify people if they're a doctor or nurse based on their names. And even if you don't know all the names, the LLM knows that the ending A of a name is more often the name for women. So what actually happens when you ask the LLM for this is it generates a feature names ending in A. And that's kind of what we thought might happen. And we saw that it does happen, that it introduces this new feature that actually makes it possible to detect the gender of people, and in that way make biased predictions or containing biases that we might not want in our algorithm. The nice thing is, though, that also for that generated feature, the LLM will tell you, well, I created that feature names ending in A because that is identifying female names. And in that way, if a person looks on at the data and the generated features, it's easier to spot this bias. But I would still say there's a lot of caution needed. And then there's also the social impact of automating even more parts maybe of data science. But I think this is a bigger issue that's really not something that we can answer in our work. So I think, yeah, this is a step towards automating more of the data science pipeline, especially of the semantic work that's actually needing contextual information and real-world knowledge. We have our code available on GitHub. There's a Python package that you can use, and it's /AutoML/CAAFE, or on pip it's just /CAAFE. And I think there's a lot of open work possible, specifically on CAAFE. There's definitely lots of ways to improve it. Maybe not relying on these closed source models like GPT-4, better feature validation, making actually statistical tests on the feature validation, whether we keep a feature or not, maybe shouldn't be based on just adding 0.001 to the ROC AUC, but doing a statistical test. I think we can learn a lot from the automated feature engineering literature still. Also, like prompt engineering, I think like trying to do that in a scientific way is something that's that would be useful. Applying CAAFE to larger data sets and better benchmarking. And I think also there is a lot of potential in applying a similar approach to other tasks like visualization or insight generation. But I think also here we need to find good ways to evaluate that, to build benchmarks, which is really hard. There's this entire field of computer-human interaction where maybe there's some recipes on how to evaluate things like that, but I think it's it could be really challenging building these benchmarks. Yeah, that's it from my side.